Introductory Chemistry, Chapter 2, Measurement and Problem Solving. Scientific notation is used to express very large or very small numbers easily and with the correct number of significant figures. It represents a number as a power of 10. The number of atoms in 12 grams of carbon is a lot of zeros there. So we don't want to have to represent all those zeros. So we are going to convert that number as a factor of 10, right? 10 to the 23rd means then that we have 23 places after the 6-point value, right? We can move this 23 places, and that is the same number as what is here. The mass of a single carbon atom in grams is a very, very small number. So we don't want to have to write out all of these zeros. So instead, we're going to move our decimal point to sit behind that very first number and then represent it as a factor of 10. So we see 1.99 times 10 to the negative 23. So n has to be a number between 1 and 10. It cannot be 10. If it's 10, then we would have to move that decimal point over again. The little n is a positive or a negative integer. So positive means we have a really big number. Negative means we have a really small number. So how do we convert to scientific notation? When we convert a number greater than 1, the original decimal point is moved to the left, and the resulting number is multiplied by 10 to that value. So once again, if it's a big number, the exponent is positive. As we see here, we move this 1, 2, 3 places to the left. 3 is our exponent. When we do this, right, and sometimes we don't know whether this 0 is significant or not, and we will talk about that later. If we're going to convert a number less than 1 to scientific notation, then the original decimal point is moved to the right, and the resulting number is multiplied by 10 to the negative x. And our x and our n here actually mean the same thing. So we have a small number here because our decimal point starts out at the beginning, right? That tells us we're a small number. We have these leading zeros that don't matter. We're going to move this 1, 2 places. That shows our exponent here as negative 2. And we have our 5.34. We don't add any zeros on at the end because we do not change the number of significant figures. So significant figures. These are all of the digits in a number that represents data or results that are known with certainty. Then you get one digit at the end that we call uncertain. So here we have 2 different measuring devices. They measure the same distance. They're both 10 centimeters. However, our increments here that we can actually see that are measured are smaller. So we're going to get a more accurate reading here than we are here. So here we know these go by ones. So we know for sure that this distance is between 5 and 6 centimeters. We then approximate what's in between, 5.4 centimeters. Here we have things going by a millimeter or 0.1 centimeters. So we know for sure that it's 5.3, maybe 5, in between 5.3 and 5.4. So then we're going to approximate between the 0.3 and the 0.4, and we say, oh, it's a little bit more than halfway, so we're going to call that 5.36 centimeters. So here we only have 2 significant figures. Here we have 3 significant figures. The more significant figures we can have associated with our measurements, the better your data is going to be, the better your calculations are going to be. But we can't make up significant figures. So we can't actually say that this is 5.36 here because we're only allowed to guess between our smallest known increment, right? Our smallest known increment here is between 5 and 6. Our smallest known increments previously were between the 0.1 marks, right? The 0.3 and the 0.4. So how do we recognize significant figures? Well, rule number 1 basically says all non-zero digits are significant. So 7.314 has 4 sig figs. 73.14 has 4 significant figures. It does not matter where the decimal point is here, or if there was a decimal point. It's going to have 4 sig figs. Here, 60.802. This has 5 significant figures, and this is what I call the zero sandwich rule, which says anytime you have zeros sandwiched in between any two non-zero digits, they are significant. So 0 sandwiches, make those zeros significant. Rule number 3, this is my to the right rule. So to the right of a decimal point, to the right of a non-zero digit, whether the digit is after the decimal point or before the decimal point, it's still to the right, to the right. So anytime you have zeros after a decimal point that are after another number, those zeros will always be significant. So here, this kind of goes back to the zero sandwich rule. However, we're looking at the fact that these zeros are kind of to the right of a non-zero digit, but to the left of a decimal point. So for example, if we did not have this 8, 9 here, but we just had the decimal point, that would mean that all of those zeros were significant. So that's our rule 4, right? Zeros that come before a decimal point, before the decimal point, but after a non-zero digit are significant. Rule 5, all leading zeros are not significant. So anytime you have zeros that lead in, we ignore those, right? So this has 2 significant figures. And I forgot to mention up here, right? This number has 6 significant figures. Our last rule here, this is the ambiguousness that we talked about, or ambiguity of numbers. Are these zeros significant or not? We don't know because there's no decimal point. We don't know if this was exactly measured to be, let's see, what is that, 10 million? Or if this number was rounded, and which of those numbers were rounded? Was it, 10 million and 1, and then they rounded the last place? We don't know. So we try to stay away from using ambiguous numbers. We put things into scientific notation to help us with that. So how many sig figs are in the following? So we're looking here. We always know that numbers 1 through 9 are significant. So we know we at least have 2 sig figs here. Then we look to see, okay, these are trailing zeros. They are to the right of a number, to the right of a decimal point. So all of these values are significant. So we have 1, 2, 3, 4, 5, 6, 7, 8. 8 sig figs. Here we have our zero sandwich rule. So we count all of these numbers, 4 significant figures here. Number 3, here's our ambiguous number. Are these zeros significant or not? We don't know. So the correct answer would be any significant figures between 2 and, let's see, 1, 2, 3, 4, 5, 6, 7. So 2 sig figs up to 7 sig figs. Any one of those answers would be correct. Lastly, here we're looking at combining a couple different rules, right? So we have a zero sandwich, we have trailing zeros, we have leading zeros. So which of these zeros matter? Well, these are the zeros that don't matter, right? Sandwiched, yes. To the right, yes. So the number of significant figures in this value is 6. So there's 2 types of numbers that we're going to talk about because that helps us to determine significant figures. Inexact values or inexact numbers are things that have been measured with a meter stick or a thermometer or a balance. Anything that you can measure is going to be an inexact number because we know that that last digit was approximated, has uncertainty associated with it based on the measuring device. Exact numbers are counting numbers, pages in your book, students in the class, number of trials. So exact numbers have an infinite number of significant figures. So when I'm looking at these, then I don't say, oh, well, it's just 3, so there's 1 sig fig. No, it's 3.000000000, etc. So that this is exact, this is exact. We don't have half of a student. You exist or you don't, right? There's so many pages in our book. They're either there or they're not. So once again, measured values, inexact. counting values exact. So now how do we apply significant figures to calculations? Well, with addition or subtraction, you cannot have more digits to the right of the decimal point than any of the original numbers. So basically what we're saying here is we don't care what's in the front. We care what comes after. So you just do the addition, you do the math, put it in your calculator. Calculator spits out an answer. Well, I look here and I see that my bottom value only has one significant figure past the decimal point. This one had 3. 1 is less than 3, so 1 wins. So we round to 90.4. Same rules for subtraction. I put it in my calculator, I get an answer. There's 2 significant figures after the 3. There's 4 significant, there's 4 significant figures here after the decimal point. 2 is less than 4, so we round to 2 places, meaning these first 2 here. The 6 rounds the 8 up to 9, so our answer is 0.79. Now, with multiplication or division, we consider the whole number, the entire value that's there. And we always are going for the one that has the smallest number of significant figures. This is because we cannot be more exact than our least exact value, or more precise than our least precise measurement. So here I have a total of 3 sig figs. Here I have a total of 5. So my final answer can only have 3. So for 3, I'm looking at what does the 3 do to the 5? The 3 does nothing to the 5, so we end up with 16.5, our 3 sig figs. With division, I have 2 sig figs here. I have 3 before the decimal point, 2 after, which is a total of 5, right? Because we're just looking at the whole number here. 2 sig figs, 5 sig figs. Which one wins? 2. So when I'm looking at this value, right, I have to remember that leading zeros don't count. I'm concerned here with the 6, 0. Those are my 2 sig figs. I look at what does the 6 do to the 0, and it takes it up a notch. So rules for rounding numbers. When the number to be dropped is less than or equal to 5, the preceding number is not changed. If the number to be dropped is larger than 5, then we increase that value by 1 unit. So let's take a look at some examples here. 61.40. We want 2 significant figures. So 61 is what I'm looking at. The 4 is less than 5, so it leaves this alone. It rounds to 61. 6.171. Well, 2 values here. What does the 7 do to the 1? It rounds it up to a 2. So 6.2. Right, and when you're looking at these things, you kind of look at, well, if I look here, is 171 closer to 200 or closer to 100? Well, we know it's closer to 200, so we would make that a 2. Hopefully that made sense to some of you guys. Down here, don't care about these zeros. Here's my 2 sig figs that I'm concerned with. I've got 494. Well, is 494 closer to 500 or closer to 400? It's closer to 500, so I make this a 5. Or I just say, hey, what does the 9 do? The 9 makes that a 5. Excuse me. Down here, I have a scientific notation number. I don't care about this over here. This has nothing to do with significant figures. This just tells me where the decimal point is. So I want 2 sig figs. I look here, 3.3. That's what I like. And what does the 4 do? It does nothing to the 3, okay? So units and unit conversion, which we'll talk a little bit more about later on in another lesson for quiz 2 star. So every number has to have a unit associated with it. And it's so important to make sure you're keeping track of your numbers and your units, right? And we want to make sure that if we've measured something on the balance, that we give it a unit of mass, right? Grams, milligrams, centigrams, kilograms. The English system is kind of wacky because the numbers aren't really related to each other. We are one of the few countries who does not use the metric system. So it's just difficult to convert because 1 foot is 12 inches. We know there's 3 feet in a yard. and it takes 5,280 feet to make a mile. None of those numbers are really related to each other. In the metric system, however, we're composed of a set of units that are related to each other decimally, and it's systematic. So they're all related by some power of 10, which means that we can employ scientific notation, or we can simply just hop our decimal points around when converting between one metric unit and another metric unit. So our SI units are a metric system of units. Your standard units for mass, we use a kilogram. For length, it's a meter. For volume, it's a liter. For temperature, it's Kelvin. So notice not degrees Celsius or degrees Fahrenheit. And in time, we look at seconds. So basic units are the units of a particular quantity without any metric prefix, except for here with the kilogram, because it just makes more sense to measure a lot of the things that we have. Like you would measure your body weight in kilograms, not grams. So here are our prefixes, and this is important in recognizing what units are bigger than other units. So these are all based off of your central unit, whether that's a meter, a gram, a liter, a second, whatever. You'll notice that kilo, mega, giga, tera are all large units, right? So a kilogram is 1,000 grams. A megagram is 1,000,000 grams, right? A gigabyte is 1,000,000,000 bytes, okay? Then we go into the units that are smaller. Well, a deci is 1/10 of a gram. A centigram is 1/100th of a gram. A milligram is 1/1000th of a gram. When you're looking at these down here, it's looking at, it almost goes opposite. I oftentimes don't like to use negative exponents because sometimes I just think they get confusing. But it's 10 decigrams in 1 gram, or it's 100 centimeters in 1 meter, 1,000 milliliters in a liter. Now, you can stick with using all of these. These are going to work out, and we're going to talk unit conversion and how we can actually apply these in the second half of this chapter.